So this is an ongoing research from the PhD student, Dimitris Radonakis, and we expect to see some results public soon in the Emotions of Environment. So we need to analyze time series of different sensors, like, for example, this one, and we have changes in the surface of the Earth. We have also changes in the illumination conditions and the looking angles of the satellite. This is very important, especially for the high-resolution images. As you can see here, this is the nadir one for Heraklion downtown, and this is off nadir. So here we can see also part of the walls. Let me zoom in here. You see this gray, this is classified, this is part of the walls which is not existing here in this nadir acquisition. And this is a problem when we have to parameterize, for example, specific looking angle sections for surface temperature and emissivity, because we need the materials. We need to know the materials. And unfortunately, there are not detailed spectral libraries of urban materials. That's why in RBSF project, we developed our own spectral library. We have field spectrodiometers and hyperspectral cameras, which is very expensive equipment. And we have samples of urban materials like this in several European cities. For example, so far we have collected more than 5,000 spectra and have grouped in more than 250 clusters. However, as you may know that the European aviation authorities and national aviation authority have changed the rules, so we cannot fly this big animal, this drone with hyperspectral camera at the cities. That's why we put the camera in a tripod, and on the vantage points, we can observe and see also the vertical facades, as you can see here in the case of Berlin. And you see here, so also this is an ongoing research from another PhD student, Yannis Latsanakis, and we expect also to see in Emotions of Environment publish this work soon. So in this, here you can see this, the spectral resolution, here's the spatial resolution, and this is our field spectrodiometer. So the spectral resolution is 1 nanometer. Here is our hyperspectral camera, ground-based. The different hyperspectral sensors, like Prisma and ENMAP, at 30-meter resolution. And this area here is the shortwave infrared. This is very, very important to identify and categorize the urban materials. But you see, standard satellites like Sentinel-2 here and Landsat have just one channel, one band in this area. This is particular, this is the WorldView 3 at 1 meter, the very high spatial resolution, but has also several channels in this specific area. So this is very useful to map urban materials using our spectral libraries. So have classification like this. So we can go in material level, or we can land cover level for Sentinel-2. But important here is that these classification algorithms are trained by our spectral library, not from image-based. So we don't collect image-based to train our algorithm, but directly from the spectral library, and that means we can implement it in any city. So we have the buildings and have also spectral information for the roofs, for example, and we can employ our spectral mixing algorithms to assign emissivity values at facades with specific materials. So the methodology is published more than 10 years ago, led by Zina Mitraka, my colleague at Ford. But now, these algorithms can be populated with spectra from our spectral library. And we have also this angular land cover, taking into account the looking angle of the satellite. We can lead to robust estimation of the surface temperature, like this one. This is at 100 by 100 meters at center of Heraklion. Speaking about temperature, you may recognize this map. It's GLA, Greater London Authority. And with red is the fraction of high fraction of impervious areas. With green is lower fraction. So we have higher fraction of impervious areas here. And you see that is in line with the nighttime acquisition from Aster satellite at 100 by 100 meters. Because it's nighttime, we have a long-term collaboration with the JPL, the Jet Propulsion Laboratory in Pasadena. So I would like to thank also here the PI of Aster, Mike Abrams, that provide us a lot of nighttime acquisitions from Aster for several European cities. So this is okay for working in neighborhood scale at 100 by 100 resolution, for example. But we need more frequent acquisitions, because temperature changes dynamically. We need something like that. This is the center of London, this is Barbican City, where we have put some phenocams. This has been done by the University of Reading from the team led by Professor Sugrimod, which is my co-PI in Elsevier. And you see how the temperature dynamically changes. So we need to have, okay, 100 by 100 meters enough, but we need frequent acquisition at least several times per day. That means we need operational acquisitions, and so far, this is what exists now, the situation now, for the area of London and all the cities. So what is this? Is 1 by 1 kilometer. This is the current spatial resolution that operational satellites like Sentinel-3, MODIS, and AVHR gives. So we have several times per day. That is good. 1 by 1 kilometer is not good for an neighborhood scale, so we have developed downscalers, as this one, which is published several years ago. This research also led by Zina Mitraka at Forth, which is a nice map. This is 100 by 100 meter. This is 1 by 1 kilometer. So we have downscaled it by 2 orders of magnitude. And this is not just a nice image, but it's also an accurate one because we have evaluated against radiation data from flux towers, and you can see it performs very well, especially during nighttime. So this is the situation now, but we expect high-resolution thermal satellites. Several companies in Europe, like, for example, SatViews, Atlantis, Soratech, and especially Constellar, provide this high spatial resolution map. I like very much Constellar because they have very excellent data quality. They expect to have because these satellites will be expected to be launched soon. And this is very important for the high resolution because they have also off-nadir capabilities. And this is important because what we're interested in is this parameter. This is the complete surface temperature. In fact, this is the weighted average, the temperature of each facade, each element. And typically, the satellites see this is the nadir image. So if the satellite has off-nadir capabilities, you can see the complete temperature, which is a dot line here. You can see the evolution during the day. And you see the dot line is close to blue one, which is the temperature of the vertical facades of the walls, because the majority of the Earth's surface, the urban surface, is vertical. And the green one is the temperature of the roofs. And here is a clear underestimation during the night and an overestimation during the day. And you can see here clearly this overestimation. This from a thermal camera is 9 a.m., so it's somewhere here. So it's obvious that they have much, much higher temperature, the roofs and the walls and the complete urban surface temperature. So what we do is to have different urban structure types and digital surface models of elements. So we model, and using models like VTAF-U2 3D, for example, like this one, we can have the complete surface temperature for all vertical facades. Also, this is ongoing work by a PhD candidate. Another one, Maria Golemi, and have just submitted to Urban Climate. So the idea is just to have this type of modeling, and then from the nadir acquisition from the satellite to be able to extract the full complete surface temperature. Okay, so so far we have discussed about how we observe the urban form. But this is a combined effect of urban form and urban function. And what is urban function? Is how people moving across the city, how they meet, the infrastructure they use. See, for example, here, the dynamic population distribution in Manhattan, the weekdays and weekends. So here in lower Manhattan, weekends it's much lower. And at city scale, okay, this is Paris. At city scale, we have sensors like Tropomi of Sentinel-5P, so we can take the concentration of emissions, like NOx, for example. So this is at city scale, because the resolution enables us to do it at city scale. But the problem is that we need to go intra-urban to take the intra-urban variations and to work on urban-rural gradients rather than only urban-rural difference. And the problem is where exactly to put the instrumentation to capture this difference. In other words, where exactly the city's boundaries are. So this question, there was a long debate about this question, related and between the urban planners and planning community and hard science, the meteorology and climatology, and all this community. So in our recent publications in BAMS, which is the bulletin of the American Meteorological Society, we have resolved this by getting the radial decays in homocentric cycles from the center of parameters related to urban form, for example, the building area fraction, the vegetation fraction, the building volume, but also parameters related to urban function related to population density, the anthropogenic heat flux, and put these boundaries here when we have the changes. And see, for example, in Berlin, based on this approach, we have divided the city, the 3 rings, because we have put the thresholds here in 60 kilometers from the center and 18 kilometers from the center. And this approach helps us to know where exactly to stratify the deployment of our instrumentation, or exactly how exactly to define the domains of our modeling procedures. So, for example, I have put all this instrumentation, and this task was led in Herbisphere by Professor Andreas Christen from the University of Freiburg, which is my co-PI in Herbisphere also. So I have put automatic LiDARs and ceilometers that from this instrument from aerosol backscatters can give us the height of the boundary layer, or Doppler wind LiDARs, you can sense the 3D vector of the wind, some trackers for the radiation, and large appendix scintillometers that we can sense at large areas, a neighborhood scale, the sensibility flux, the turbulent sensibility flux, and typical flux towers. I will give you an example here. So this is Berlin, and the rings, I have replaced all these instruments. The wind blows this direction, so this is upwind, and this is the blue location for a ceilometer. And you see the backscatter and the height of the boundary layer, the evolution of the boundary layer, at here upwind at this point, and during the nighttime, the boundary layer is compressed, and then we have the turbulence and the convection, so have higher boundary layer during the day. For another ceilometer, which is located here, downtown, you see the evolution of the boundary layer above the city. That means it is higher than is expected, so we have the creation of the urban dome, and even during the nighttime, you have this boundary layer that is high in comparison to the other one, upper one. And from another one, ceilometer, which is downwind, red one, you can see it is even higher during the day, and this is indicative for the urban plume that is formed because of the existence of the city, and this way the city affects the regional climate. Or the rings help us in our multi-scale campaigns in Berlin. 2 years ago, we organized a multi-scale surface temperature campaign, and using, of course, satellites and downscale products. The rings help us to identify the roof buildings to put the thermal cameras, fly the drones, and have the campaigns with ground scanners, and also organize an airborne campaign together with SATU, and this is the path of the airplane. It is related to the location of the specific rings we have identified for Berlin. So we have detailed information from all instruments of Earth observation, and use it to parameterize and to evaluate models. So we have coupling for several models. We have a couple human exposure and vulnerability models with urban surface models, with class immersion scale models. So I will not focus on model activity because this task is led by the University of Reading, the group of Professor Sugrimond that make this coupling. But here, just to mention, we have two-way coupling of this model. So information flies from 2 directions. And Earth observation is, of course, the model. The rings are help us to identify the different domains of the modeling, and Earth observation to populate the models. So we need a buffer around the city. The city is here. You see the administrative boundary. And we need a buffer about 200 by 200 kilometers around Berlin, be able to model Berlin. And we gave to modelers detailed disaggregated information about urban form at the scale of 1 by 1 meter, the resolution 1 by 1 meter, covering all this huge area, which is covered a part of Poland, as you can see here. The border is here. But we need to calculate, and also for urban function, because we have commuting for people. just commuting every day from Poland to work in Berlin. So you have to capture all these activities for mobility and patterns, etc. So again, in the publication in BAMS, we can see how the sensors, all these sensors are deployed in Berlin, and here how the models are used with the different domains. So we have global models at the resolution 10 by 10 kilometers, and then we have nested regional models at the resolution of 1.5 by 1.5 kilometer to 300 by 300 meters. It is here, and within the rings, the inner city, we have the resolution 100 by 100 meters. And you see how a rural pixel is modeled and observed, or an urban pixel here, how is modeled and observed. And we have the observations to evaluate these models. For example, you can see the fluxes of radiation and sensitive heat flux and latent heat flux. So the lines are the modeling outputs, and the dots, what we have observed. And you see that are close enough. See, for example, the radiation, and here the sensitive flux that peaks earlier in green. The green curve is for rural, the orange one for the outer city, and the brown one for the inner city. So here the QH peaks earlier and later here, but higher, and later in the inner city, as it was expected. What is impressive is the simulation of the height of the boundary layer, and see how well these observations at these specific points that we have put the ceilometers and the Doppler wheel lidars are in agreement with the model outputs. And probably this is the first time we have such a dense network in a city, deployed in a city with so many ceilometers and Doppler wheel lidars in this Berlin campaign. Of course, at city scale, you have also the satellites. And this is, for example, the urban plume as sensed by Tropomi. And we can compare the models at different rings with surface temperature derived from satellites like MODIS, for example, and see the daytime and nighttime. So we have good agreement here. Here we have cloud cover, so maybe you have distance estimation and not good agreement for the outer cycle. At the disagreement, you see the inner cycle is probably what I described before, that the satellites is just another and not the complete surface temperature, that during the nighttime we have an underestimation of the surface temperature from the satellite acquisitions. Okay, this way we can observe and model both urban form and urban function, and represent some applications related to climate change mitigation at local scale. And speaking about mitigation, of course, we focus on carbon emission. And you see here, down from the carbon metabolism in cities, we have the later fluxes of food resources and fuels and outputs of waste and goods. But let's focus on vertical fluxes. So the vertical flux of CO2 is the emission of CO2. And our role as Earth observation community is to monitor what is happening in the cities. And for this, we have used flux towers. This is an example of Heraklion. We'll put about more than 30 meters on top of the buildings. And we have electrovariant systems for the turbulent fluxes, and we have radiometers for the radiation fluxes. And with these instruments, we can, with open path analyzers or closed path analyzers, sense also the emissions of CO2. And this is the footprint of our flux on Heraklion. This is Heraklion City, and this is Heraklion downtown, the central business district. And you see a typical daily profile for CO2 emissions. So this green part is from the upper part of our footprint. This is the source area of the flux tower. And this is typical bimodal curve with a typical here morning maximum and secondary maximum in the afternoon. That means this is driven mainly by traffic, by transportation. And this is from commuting during the morning hours. The purple curve is from the lower part of the footprint. It's a residential area, so the typical we have the afternoon maximum, which is driven by emissions from buildings, from space heating. And in our publication in remote sensing environment, in atmospheric environment, led by Stavros Tagakis in 2019, we have documented that about more than 50% of the emissions at this particular area of the city are driven by transportation. few years ago, during the lockdown period, that was confirmed because we compared emissions from different flux towers at different European cities, 10 European cities. That was a study that was very much like from the WMO, so they put it in the cover of WMO bulletin, but it's also published in Science of the Total Environment. And here you see several examples for the cities that have flux towers. With red curves, we see the profiles 3 or 4 years before the emissions, the daily profiles. And with the red one, the curves, we can see what was happening during the lockdown period. And you see, for example, in Heraklion, because the flux tower is downtown, we have the higher emission, about 75%. And you can see it better here compared with Basel in Switzerland. We have here also around 44% reduction. But here, even during the lockdown period, we have emissions from building because people were inside the building, and we need what was February or March, that was the month for space heating and consume fuel for buildings. That's why we have emissions for buildings. That was not the case in Heraklion downtown. And our flux tower is also flexible to changes. For example, local authorities have just made this intervention, pedestrianize the central part of the city. So that was within our footprint, this intervention, and our flux tower was sensitive, so we were able to identify the measure and document to report to local authorities the reduction of the CO2 because of this urban intervention in the cities. Okay, this is byproduct, and what is really important is this. So this is the flux tower in the center, and it runs for more than 10 years. 5 years ago, we deployed a second flux tower here. Both flux towers are labeled by ICOS. ICOS is a big European infrastructure, is the International Carbon Observation System. And all over Europe, there are only 7 flux towers, urban flux towers, labeled by ICOS. Because the labeling procedure is very difficult, you should have super data quality to get the label by ICOS. And I'm proud to say that we run 2 out of 7 European urban flux towers in Europe. And you see the footprint again, as identified by my colleague Konstantinos Politakos. And you see that the first one is, we were discussing before, the central business district. You see the different buildings, the mixed-use building and the high building that we have here. And this is a pure residential area. And this is a unique setting for our research, because we have 2 flux towers, which is about 1.5 kilometers apart from each other. That means, in practice, they have almost identical meteorological forcing, but they are located in areas with different urban form, and different function. So we expect to have different CO2 profiles. And this is true. You can see the daily profiles. You can just remember the red curve from this flux tower. This is the morning maximum and the bimodal curve. And this is more or less the same throughout the year because it's driven by traffic. Here for the residential area, we have completely different profile with secondary maximum, but you can see that this is different across the year, and this maximized during the summer, during the winter months, because there we have emissions from buildings because of consumption of fuel from space heating. And this is the 2 extremes. So every other point in Heraklion is somewhere between. And we can use this information to model. And this is a model for the CO2 emissions we have made for Heraklion. My colleague Manuelis Panagiotakis worked on this, and a paper just submitted on this modeling to atmospheric environment. And we are able to report this for Heraklion, but also for other European cities. So as soon as I go back to Greece, I will start a new Horizon Europe project. I have been awarded. I have the honor to lead this project, and for the next 3 years, we generate this type of modeling for the cities that have joined the European mission for 100 smart and carbon neutral cities. Okay, so we are able to monitor the progress of Heraklion towards its carbon neutrality or climate neutrality But even these emissions are completely removed, the temperature of the city will not change because climate change is a global phenomenon, and all cities should, and all sectors of the economy should reduce their emissions, and then we need some decades for the system to stabilize and the temperature to start reducing. So I have heat waves like this, and this is the evolution, the temperature. This is at 11 p.m. And you see it's around 30 degrees when the definition for the tropical night for the cities like Heraklion is when the minimum temperature is higher than 20 degrees. So there was a huge heat wave 2 years ago. I have not the experience of what we have in Heraklion because I was again here visiting Yale until July 2023. But we know that this phenomena will become more frequent and with higher intensity based on the last IPCC report. So we need to adapt. And we need, when we say we need to adapt, the adaptation is related to energy budget. And again, in the control volume, we have net radiation, the energy coming in the system. That means it's short wave minus long wave radiation, and that is stored in the system. And we have another input, which is the QF, this is the anthropogenic heat flux. That means energy that is coming from emitted from buildings and from transportation and the human metabolism. So these are the inputs of the system. And for cities like Heraklion, this is small. But for cities like Tokyo and New York, can be in the order of magnitude of 800 watts per square meter. That is comparable to Q star. So this is the energy coming in the system, and then it's stored in the system. So we have a change in heat storage in this volume, mainly in buildings. And then a part of the system is used, is transported by the turbulence, the eddies of the turbulence to the air. Because the temperature of the surface is higher, the temperature of the air is lower, so we have a gradient of the temperature, and whenever we have gradients in nature, we have fluxes. So we have gradient of the temperature, we have the heat flux. So this is the mechanism that the temperature of the air is increased. And another part is used to evaporate water. This is the evapotranspiration, or the turbulent latent heat flux. So we use Earth observation to estimate each of these terms of the energy balance separately, as we can discuss later. But now the local authorities need to reduce this term, because this is, as I told before, the mechanism that increase the air temperature and the thermal discomfort in cities. However, this is not, they cannot directly they cannot directly do it, and they cannot intervene this term. But since we have a balance, they can instead increase the QE. How we can do it? By increasing the green and blue infrastructure in the city, by green walls, green roofs, and streets, etc. Or they can go the other part of the equation here and reduce the Q star. How can we reduce the Q star? By using cool materials or super cool materials or techniques like daytime radiated cooling. Or they can reduce this term, the QF, how? By using better insulation in buildings or different traffic regulations. So we have solutions like this. They have that include nature-based solutions. This is a guide for deploying nature-based solutions we have published 4 years ago. It is available through our website. You can download it. But now we can even see the deployment of new technologies. So this is work with very high resolution. 4 years ago, this is the industrial area of Heraklion, and this is the situation that was a few months ago, in 2024. And you see how the solar panels have been deployed on the roofs of this industrial area. And this is the result of the Greek National Energy and Climate Plan that gave incentives to the private sector to build these solar panels. But we have our spectral libraries. So we have the spectral signature of the solar panel, measured with our field spectrodiometer. And Yannis have adjusted to the channels of worldview 3. And you see, this area here is very important, as I have explained before. And you can use a combination of channels of worldview 3 at this area. This is, for example, the shortwave channels. You can much more easily detect the solar panels. Or we have developed classifiers using the spectral library. So we have spectral material-based classification like this. So we can detect everything. And this is true because we have developed the spectral libraries. And we can parameterize radiation models like DART, for example, a very detailed CFT type model developed by our colleagues in France in CESBio, Jean-Philippe Gastelot-Chegori and his colleagues. And we can model the albedo at 1 by 1 meter. So the albedo is the total reflectance, but we have also the angular integration. The problem is how to go from 1 by 1 meter to the neighborhood scale, let's say 10 by 10 meters. Because this is not just a linear upscale, because we have the effect of the bulk albedo and we have the multiple reflections. So in order to do it, we just simulate from 1 meter and upscale a single direction, which is the satellite image acquisition, the Sentinel-2, and then compare it with real satellite Sentinel-2 acquisition, and produce an error map like this. And then we can use it to upscale the albedo at local scale, which is the satellite scale. And since we have it at local scale, we can produce maps for the whole cities like this, which is day and night, the net radiation, which is the most important term of the energy budget. Or the storage flux, the storage, the net change of storage, we have a picture like this. So here is the derivative of temperature, how the temperature changes with time. So if we have thermal cameras at different facades at different orientation, we can have this information. And this is the thermal mass. Again, we have the spectral library information about the width of the walls and the edge of the building. So we can also have the thermal mass. And the difficulty is the FI, which is in each pixel, the fraction of all elements, the fraction of roofs, the fraction of vegetation, the fraction of walls of the ground, and this is coming from our 3D city model. So have all this data, you can calculate the delta QS. This is an example from Heraklion, and it's highly correlated, of course, with the existence of buildings. In here, the city downtown at 100 by 100 meters. Okay, you are not familiar with Heraklion, but you may be more familiar with London. And this is a land cover classes in London, and with red you can see buildings. And here this is the output of our model. It was published in our publication Scientific Reports 5 years ago. And you see in these areas we have skyscrapers and high buildings. The delta QS is much higher. And also here, which is the area of, here is city, here is the area of Canary Wharf. So we have also skyscrapers here. After the organization of Olympic Games of 2012 in London. Okay, and another example, that is a master plan for a panel in a park, small intervention in the city of Heraklion. We modeled the turbulent fluxes, so this is the map. Imagine that is, we turn it clockwise, and this is just the area, the small area, the map, so we'd like to test the methodology. And we run such model with parameterized for the current situation, and this is the different land classes based on the master plan that gave us by the local authorities. And we run in a grid like this at 100 by 100 meter, and we see how the different land coverage changes and the different fluxes of the energy balance at these specific cells. And it's important to see that only here the central pixels, the central cells, the change in fluxes is important. That means the effect is quite local because it's a small intervention. That means in practice we need much higher interventions in cities. So we have used all this information about the surface temperature and thermal comfort and heat storage to build applications in DIAS, in VKO. This is something like Google Earth Engine and Amazon, so it's the European cloud. That was in the frame of the Cure project, and we have built all these applications. And this is related to urban resilience, and you can have access to see that we have done in several European cities. For here, we give you an example for air pollution. So I use Copernicus atmospheric service and land monitor service, just to have the background information about air pollution, the urban background also, and measurements from traffic peaks. So in practice, we downscale what is come from ERA5 and from CAMS to local level. And this is an example from NO2 coming from transportation that you can see in the city of Sofia, in Bulgaria, This is correlated with the cities. And here, another map from the same city, the PM 2.5, that is coming mainly from buildings, from central heating. So you can see the different patterns here. So this is easy. We use the atmosphere map, which is from my colleague Vito. And now, in Greece, we have new satellites, and we are responsible for the air quality and several urban applications. We replicate the same, but using AI instead of atmospheric modeling. The same approach for floods. We have coupling hydraulic with hydrologic model for Heraklion. We have inundation maps, and we have in our GIS our different land cover types, and we have the building information just to have the hazard and vulnerability information to have risk maps for each specific buildings and area in Heraklion. And maps for thermal comfort. This have the indices like this, which is the wet bubble global temperature. This is a map for San Sebastian. You see we have high temperature here, again from Cure. But you can measure. We have sensors like this. That means in practice we are measuring simultaneously the air temperature, the wet bubble temperature, and the black bubble temperature. That means the humidity, the temperature, and the radiation. And we have curves like this. This is for the heat wave in Heraklion, and this is the shaded area under the trees, and this is the open area. You see the difference, and you see the thermal discomfort is much, much higher here in this area. This is very important, the services, the cooling services by vegetation, provided by the two mechanisms, the shading, of course, and the evaporative cooling, the turbulent latent heat flux. This is evapotranspiration. So we can have information about thermal comfort and measure it and model it, but how it correlated with the perceived heat, the perception of heat with people. So back to Berlin again, back to rings, and this is the different urban structure types in Berlin at the percentage of in different rings. And then in Berlin, we organized in Herbisphere a household survey that was led by Professor Jörn Birkmann from University of Stuttgart, which is also my co-PI in Herbisphere. So he sent 10,000 questionnaires to people in Berlin, and we get back 1,000. Okay, just finishing. Okay, get back about 1,000 questions. We analyze it, and you see that the balance here, the thermal comfort, is displayed by the city, and the perceived heat, and they are in line, although we have different violins. And here with the bars, the red bars, that means the people have responded that the neighborhood is much hotter than and warmer than the average, and here with blue it is cooler than the average. So we see that both thermal comfort and perceived heat are changing and are reduced as we remove from the center of the city, but this is not the case from the human vulnerability. From the same questionnaires, we have maps like this, where most vulnerable people live. The elderly people, that means people which is older than 65, and most of them lives in ring C, ring B, this is the inner cycle, and the different structure types, urban structure types, the buildings types that they live. So people that live here, so lives a road development of semi-detached houses, so they have probably access to green services, to green spaces, or they have much higher adaptive capacity. But there is a high percentage, about 25% in Berlin, that live in high-rise buildings, mainly here. And for these people, the Berlin Senate, the local authority should just give special care during heat waves. This is a matter of environmental justice. And last slide, just to present also a study that we have recently published in Nature Cities, led by Professor Rocha from TUB. We have combined the radiative cooling and evaporative cooling for vegetation. So this is the cooling surface of vegetation, normalized from 0 to 1. So this is good, this is poor performance. And here is the percentage of residents with 40% lower household income. That means, which is red, is higher percentage of poor people live here. That means it's higher here in, for example, in Paris and London, or center of the city in Amsterdam and Vienna, and the west part of the city in Athens. And you see in these areas, the cooling services by the vegetation green is much lower, it's poor. So this is very important. This is disaggregated information for the 13 European capitals, and this is useful for local authorities, and we have also ranked the cities, and here we have the cooling service index, and you can see, for example, that in Athens, 80% of the population lives in areas where this index is less than 0.5. That is, these two categories. And only in these three cities, which is Helsinki, Budapest, and Stockholm, half of the population enjoys good cooling services by the vegetation because the index is higher than 0.5. Okay, I can stop here just to summarize and give some take-home messages. So first one, the Earth observation has a key role to developing climate services, to build urban resilience and to inform policy making, to inform also reports like the IPCC report we expect on cities and climate change, which is expected that the next couple of years. However, the urban research, the urban climate research needs to better exploit the Earth observation to address key knowledge gaps and key research questions. For example, need to better understand how to link the different spatial scales, or how to couple urban form and urban function, because urban function continuously changes in the times of seconds, and urban form changes in the months or decades, etc. Or we need to understand the feedbacks between cities and climate change, how cities affect the boundary layer, and how this boundary layer affect the climate, the regional climate and global climate. So the Earth observation has the potential to improve, capture the complexity of the urban dynamics, and to support the urban climate community to change the way we represent cities in climate models. So to go to the next generation of climate models, we'll know very well that cities are not included in the foregoing simulations of IPCC. So all these projection scenarios, it's an area that we downscale and use for cities. Very simply, they not contain cities in the form of simulation. And for this, the new satellite sensors for both mitigation, like CO2M, and adaptation, like LSA and CHIME, will be game changers. And this is related to measuring the emissions of CO2, related to mitigation, and this is very high resolution surface temperature and the hyperspectral sensor. These are launched by the European Space Agency, but I know very well that other space agencies like NASA, JAXA, and the private sector also have launched atmospheric sensors, and we expect more sensors in the coming years. Okay, so thank you very much for your attention. I'm available to discuss and to respond to any questions, and I'll be around until the end of December, and very happy to talk to any one of you next days or the next week or whatever. Thank you very much.